communications are down. There is no electricity. There is no internet. There is no telephone. What are we going to do?
If only we had a Morse code translator.
Oh my God, we found it!
If only we knew someone who could figure this out. I have come to the rescue.
The aim of our project was to create a dual Morse code translator. Morse code was invented in the 1800s, encoding the English alphabet into a series of dots and dashes. The alphabet that appeared frequently in a language takes the smallest encoding. For example, E takes a dot and the Z takes a dash dash dot dot. The thing about Morse code is that it gets through, meaning even if there's very high interference or noise, Morse code gets through because it needs very little frequency. Our system translates in both directions, from English to Morse code and from Morse code to English, as our colleagues will demonstrate.
Contributed equally in our project. We did not divide it into subparts. The complexity of our project was not in the hardware, but it was in the software, because as you can see in the hardware, we're only using the FPGA Altera board, a PS2 keyboard, and the buzzer. However, the coding part was very challenging because it was hard to detect the sequence of dots and dashes entered by every user, as it is subjective and it's not something constant. And the other challenging part was displaying the characters entered by the button on the LCD because it was hard to update the characters constantly.
The direction from English alphabets to Morse code goes as follows. We're using a PS2 keyboard which sends the ASCII code of the character pressed to the FPGA, which we then read using Verilog code. And then each character in ASCII code is translated into another code as a sequence of ones and zeros. 0 for the dot and 1 for the dash of the Morse code. And then this code is sent to the module responsible for operating the buzzer. And then we simulated the dots and dashes using timers of different lengths with a short period of silence between every dot and every dash.
So when this switch is on, we move to the other direction where we translate from Morse code to the alphabets. As long as this button is pressed, we send signals to the buzzer to simulate the sound of dots and dashes, and this delimiter denotes the end of the character we send. We designed a finite state machine to detect the dots and dashes based on the period of time this button is pressed. We use the threshold to differentiate between the dots and dashes. Everything below this threshold is considered a dot, and if it exceeded the threshold, it will be a dash. Those dots and dashes are encoded into strings of zeros and ones that will be translated into characters according to the Morse code encoding. Those characters are sent to the LCD through a buffer that can be cleared if we want to reset the LCD, and that's it.
We were having two directions, one that translates from Morse code to alphabet and the other translates from alphabet to Morse code. And the direction is determined using this switch. Now I will explain the direction from Morse code to alphabet. We send the code using this button where the long dash will be where the long beep will be the dash and the short one will be the dot. So for example, we're having, then we use this button to separate between the alphabets and to display the character on the screen. Then we have this button that clears the LCD.
And now I'm gonna explain the other direction from text to Morse code using the keyboard and the buzzer. Now I'm going to change the switch. And I'm going to type SOS, the previous signal that Nurhan made earlier in the video. And that's it.